Okay. Oh, we will go through some important points in the class 12 physics chapter 13 nuclei. Okay, so here are some important things from this chapter. One atomic mass unit, 1U, equal to the atomic weight of the carbon 12 isotope. That is, carbon exists in different isotopes. So we are taking C12, then divided by the 12. Okay, though you will get the one atomic unit in terms of kilograms. Okay, 1.66 into 10 power minus 27 kg, that is equal to one atomic mass unit. An atomic mass unit in kgs. Okay, what are isotopes? Isotopes, they have same number of same atomic number but different mass number. Okay, example, this hydrogen isotopes, proton, deuterium and tritium. Okay, these are all same Z, that is same atomic number, but they have the different mass number, that is 1 2 3 mass number. Isobars, in isobars they have the same mass number but different atomic number. Okay, here you see helium mass number 3, hydrogen also mass number 3, hydrogen one of the isotopes, mass number 3, same mass number but different atomic number. Here one atomic number, here two atomic number. There is isotones. Okay, they have same number of neutrons. Okay, so here same mass number, here same atomic number, here same number of neutrons. So here if you take this as 79 protons, 79 electrons. Okay, this number is protons plus neutrons. Okay, 79 plus something equal to this number, so that means 118 neutrons. Okay, 118 plus 79 is 197. So here this is 118 neutrons. Similarly here also 80 plus 118 is 198. This, so here also 118 neutrons. They both have the same number of neutrons, that is isotones. Okay, this is the relation between the radius of the nuclei and their atomic mass. Radius of the nuclei equal to R naught into atomic mass power 1 by 3. Okay, R naught is a constant value. 1 femtometer is equal to 10 power minus 15 meter. This is the mass defect. Atomic number into mass of proton plus atomic mass minus atomic number into mass of neutron minus the atomic mass. Okay, then delta m into c square is the binding energy. This is binding energy per nucleon. Binding energy divided by the atomic mass is binding energy per nucleon. This is used to compare stability of the various elements. Okay, more binding energy per nucleon means more stable compound. Nuclear force is greater than the Coulomb force between the charges, and this is greater than the gravitational force. Okay, what is fission and fusion? Fission, we are breaking the heavy nuclei into two fragments, atomic fragments. This is fission. Fusion, we are combining light nuclei into heavy nuclei. Okay, fusion are opposite things. See, this is, you have already seen what is the ratio between the volume of the nucleus and the volume of the atom. Okay, so nucleus contain most of the mass of the atom. Okay, that is 99.9% of the mass of the atom is in the nucleus. So this is the 1 AMU atomic mass unit Okay, I already shown you. These are isotopes. They have the same chemical properties, differ in the mass. That is same atomic number from different mass number. These are the isotopes of chlorine. So how do you find the weighted average of masses? Weighted average of the atomic mass. So hydrogen has three isotopes: proton, deuterium, and deuterium. Three isotopes of hydrogen. Z is the number of electrons, that is equal to the number of protons. Number of protons and number of electrons are equal. So this is E is the charge on a single electron. The total charge is Z number of electrons into E. Z electron is Z proton. This is positive charge, this is negative charge. So the new particle neutron is mass of the neutron is equal to the proton's mass of the proton. Z atomic number of protons, n neutron number equal to number of neutrons, atomic mass number equal to number of protons plus number of neutrons, Z plus n, that is the atomic mass number. These protons and neutrons, they are generally called nucleons. This is how we represent the element with the atomic mass on the top, atomic number on the top. So if you take the isotopes of hydrogen, they differ in the number of neutrons only. The atomic number will be same, one only, but the atomic mass is different because of the different number of neutrons. Okay. First isotope have 1 neutron, second have 2 neutron, third 3 neutrons. Isotopes given contain the same number of protons but differ in each other number of neutrons. Okay, sorry. So this deuterium has 1 proton and 1 neutron. Okay, here 1 proton, 1 neutron. The other isotope contains 1 proton, 2 neutrons. Okay, they differ in the neutrons. Here 1 neutron, here 2 neutron. All the isotopes, they have the same electronic configuration. That is important because this atomic number is same. So their isobars, they have the same atomic mass but different atomic number. Isotope, they have number neutrons. This is how this radius of the nuclei and the atomic mass relation. Okay. The important thing is that the density of the nucleus is independent of its atomic mass. Okay, density of the nucleus is constant independent of the atomic mass. That is important. It's independent of the atomic mass. Given the mass of the ion, okay, A equal to the nuclear density. Okay, here we are multiplying the atomic mass into 1 unit in kg, 1.6 into 10 power minus 27 kg. Okay, I already shown you. So then after multiplication you will get this number. Volume 5/4 pi r cube. This r is taken from this formula. You have to use this formula. Here the A is there, okay. r cube will come, a power 1 by 3 into 3 will cancel out, so a, that is this a. Density of matter in neutron stars and astrophysical object is comparable to this density. This shows that matter in these objects has been compressed in such a extent they resemble in big nucleus. This is Einstein's mass and velocity of a relation. Mass into the how mass is converted to the energy. 1 gram substance, how much energy is there in the 1 gram substance? Enormous amount of energy. So here in the you see the mass number is number of protons plus number of neutrons, but there are electrons also there. So the atomic mass of this is oxygen found from the mass spectroscopy experiment is only 15. So here if you compare these 8 neutrons, protons plus 8 electrons, then you will get the total mass, okay, for the oxygen, but it is found that it is the mass is around 15.9 because this number will come after subtracting the electrons, okay, subtracting the mass of the 8 electrons we get the experimental result. So that is why we are excluding the mass of the electron. We are considering only protons plus neutrons. The difference in mass of the nucleus and its constituents is called the nucleus and its atomic constituents is called the mass defect. How delta m is related to the energy. The energy equivalent of the 1 atomic mass unit, 1 EU, how many mega electron volts? Okay, 1 E equal to this many kgs. To convert this, okay, this many kgs into delta m into c square, velocity of light, 3 into 10 power 8 meter per second. So this is square. So now we have to, this is in joules, we have to convert the joule into the electron volt. Okay, this is electron volt. This electron volt you have to convert to the mega electron volt, that is 10 power 6 mega. Okay, so in the future reference you can directly use this number, that is 1 unit equal to this many mega electron volts. Okay, 931.5 mega electron volts. This is called the binding energy, EB. Binding energy per nucleon is divided by the atomic mass. This is this factor, binding energy per nucleon, is measure of the stability of that nucleus. Okay, more energy means more stable, that is binding energy per nucleon, more means more stable. Normally it is 8 mega electron volts. Okay, this is that one. So that is the average binding energy per nucleon is normally 8 mega electron volts. In this curve is atomic mass number versus the binding energy. Okay, and this curve is differs when A is less than 30 and greater than 170, less than 30 here, and A is less than 30 around here, so binding energy is less. Similarly greater than 170 also binding energy, but in between almost constant, 8 mega electron volts. Light nuclei, A atomic mass number less than 30 and heavy nuclei greater than 170. When the distance is less than this r naught, the force is repulsive, and the distance is greater than the r naught, the force is attractive. Okay. For a separation greater than r naught, the force is attractive, and separation less than r naught, force is repulsive. The nuclear force is greater than the Coulomb's force, greater than the gravitational force. For distance between the distance of the larger than the 0.8 femtometer, the repulsive, it is measured by the distance less than the zero point 0.8 fm. If it less than, then it is repulsive. Greater than means attractive. These are the decay: alpha, beta, gamma decays. Fission and fusion. When heavy nucleus decays into more intermediate mass fragments, this is fission. When light nuclei fuse into heavier nuclei, that is fusion. Nuclear energy is much higher than the chemical energy. Okay, this is the comparison. 1 kg uranium generated this much of joules of energy. Compare with the burning of 1 H coal, only this much energy. This is fission. Okay, we are splitting the heavier nucleus into smaller things. Fission, when uranium is bombarded with a neutron, breaks into two intermediate mass nuclei. Okay. This is equivalent is nothing but the energy release. This is fusion. Thermonuclear fusion is the source of energy in the output in the interior of the stars. Okay, the fusion reaction in the sun is a multi-step process in which hydrogen is burned into helium. Okay, in the sun, hydrogen is burned into helium. Smaller nuclei combine to form a larger nucleus. Fusion. Hydrogen burned into helium. This is how the equation is balanced in a nuclear reaction. Okay. So the number of protons and neutrons are equal here. Okay, on the left side and the right side. The age of the sun is this many years. It is estimated that there is enough hydrogen for the sun to keep it going for another billion years. Okay, billion years. Or the equation of the nuclear reactions such as those given in the balanced, in the sense the chemical reactions they are balanced like this. No, they are balanced with protons and neutron. A chemical reaction is balanced in the sense that the number of atoms on the each element is same on both sides of the equation. That is for the chemical reaction. Okay, chemical reaction merely alters the original combination of the atoms. In a nuclear reaction, the elements may be transmuted. Thus, the number of atoms on the each element not necessarily conserved. Number of atoms need not be conserved. In a nuclear reaction, however, the number of protons and the number of neutrons are both separately conserved. I already showed you number of protons and neutrons are conserved. Actually, even this is not strictly true in realm of very high energies. What is strictly conserved is the total charge and the total Baryon number. We need not pursue this chapter matter here. In a nuclear reaction, the number of protons and the number of neutrons are same on the two sides of the equation. Okay, number of protons and neutrons same on the two sides of the equation. I already shown you. If both number of protons and number of neutrons are conserved in each nuclear reaction, in what way the mass is converted into energy or vice versa in a nuclear reaction? How energy is occurring in the nuclear reaction? We know that binding energy of the nucleus gives the negative contribution to the mass of the nucleus, mass defect. Now, since the proton number and the neutron number are conserved in a nuclear reaction, the total rest mass of neutron and protons is the same on the other side of the reaction, but the total binding energy of the nuclei on the left side need not be same to the right side. Total binding energy may be differing on the both sides. The difference in this energy appear as the energy released or absorbed in area. Okay, difference in binding energy on the both sides of the equation is released or observed. Since the binding energy contribution to mass, we say that the difference in the total mass of the nuclei on two sides get converted into energy or vice versa. It is in this sense that the nuclear reaction is an example of a mass energy interconversion. Nuclear reaction mass energy interconversion. Okay. General impression exists that mass energy interconversion takes place only in a nuclear reaction and never in a chemical reaction. This is strictly speaking incorrect. From the point of view of the mass energy interconversion, a chemical reaction is similar to the nuclear reaction. In principle, the energy is released or absorbed in a chemical reaction can be traced to the difference in the chemical, not nuclear binding energies of the atoms and molecules on the two sides of the reaction. Since strictly speaking, chemical binding energy also gives the negative contribution to the total mass of the atom or molecule. We can well say that the difference in the total mass of the atoms and the molecules on the two sides of the chemical reaction get converted in the energy vice versa. However, the mass defects involved in the chemical reaction are almost a million more smaller than that of the nuclear reaction. Okay, that is very small. This is the reason for the general impression, which is incorrect. The mass energy interconversion does not take place in a chemical reaction. Okay, mass defect binding energy. This is the energy release Q. This is the fission example. This is the fusion. These are the dimension of the various quantities. Okay, the nucleus density is independent of the atomic number. Okay, we will go through the exercise problems. These are something data we can use in the exercise. Okay, so this is 1 unit atomic mass in how many mega electron volts. 1 mega electron volt is how much is joules. Mass of the neutron, proton, charge of the electron. Okay, obtain the binding energy of the nitrogen nucleus. So the binding energy is mass defect into velocity square, velocity flight square. Okay, this is the binding energy equation. So for that we have to find out the mass defect. So from the book formula, mass defect delta m equal to z atomic number into mass of protons, atomic mass minus atomic number into mass of neutron minus atomic mass. Okay, the nitrogen they are given, this is the atomic mass, z atomic number, a atomic mass. Then after substituting you will get mass defect in atomic units. Okay, so now using that we can find out the energy, binding energy, means velocity square. So here 1 unit equal to this many kgs. Okay, I already shown you in the book. So then you are converting this, this will come in joules. 12 to electron volt, 1.6 into 10 power minus, we are dividing to convert to the electron volt. Okay, then after that this many mega electron volt you will get. This is the equation, mass defect, and this is your binding energy. So here actually you are converting one atomic mass unit into a mega electron volt. You can also directly use this value, but I substituted like this. You can also directly use this value. Obtain the binding energy of the nuclei for this iron and bismuth. So here as compared to the previous one, we are going to find the binding energy per nucleon also, for the comparison purpose between the iron and bismuth. This is the binding energy, then binding energy per nucleon is this much. Okay, and for this is this much iron. So in this way we can compare which is more stable. This is more stable than this. This has more binding energy. Okay, we binding energy per nucleon. A coin of mass of 3 gram, calculate the nuclear energy that would be required to separate all the neutrons, protons from the coin. For simplicity, assume that coin is entirely made up of that copper atoms. Okay, with the atomic mass. So this is the atomic mass. This has 29 protons and 63 minus 29 neutrons. Okay, 63 minus 1, that means 34 neutrons. So this molar mass is 63 gram, that has these many atoms. Okay, they have given only 3 grams. Okay, 3 gram, 3 by 63 into this many atoms it has, that 3 gram coin. Okay, this has 34 neutrons. Then mass defect, total binding energy. Okay, here you see I am directly using this many units from this delta m. One atomic unit equal to 931 this mega electron volts I am using from the book, page 6. So I am using this directly here. Okay, I am using this directly. Okay, then you will get this much electron volts. Okay. Obtain approximately the ratio of the nucleus radius of the gold to the silver, gold to silver. Okay, this is the formula, radius and atomic number relation. This is constant, so this will cancel out when you take the ratio. So then you will get 1.22. So you see this relation. The Q value of the following reaction is defined. This is how we have to compute the Q. Okay, reactant minus products. This is reactant minus products, where the masses refer to the respective nuclei. Determine the given data Q value of the either endothermic, exothermic. They are asking for the following reaction. We have to use these values. Okay. Why? So based on that formula, you compute. Based on that, you compute the value. Okay, binding energy of this plus this minus this minus this plus this. Okay, these are all given. Then the energy is negative, that is endothermic. Okay, and in this case, that is coming positive, that is exothermic. Suppose we think of a fission of a nucleus into the two fragments. Okay, the fission, is it energetically possible? Argue by working at the Q value of, okay, this is, so this is broken into two fragments. Okay, this minus 2 into this energy. So this is negative, so that is fission is not possible. Okay, this energy is more than this energy. Okay, this is the energy. How you find the energy? The fission properties of this plutonium are very small, similar to that of the uranium. The average energy release per nucleon is 180 mega electron volt. How much energy in mega electron volts is released in all atoms in the 1 kg of the pure plutonium, and we undergo fission. Number of atoms in 1 kilogram of the plutonium is equal to 1 kilogram. So this is the atomic mass, molar mass of the this plutonium. So we have to see how many atoms are in the 1 kg, that is 1 kg. So into Avogadro number. Okay, so this is the average energy. So multiply this, then you will get this total energy. How long can an electric lamp of 100 watts be kept closing the fusion of the 2 kg of the deuterium. Take the fusion reaction. Okay, fusion reaction. Number of atoms in the 2 kg of deuterium. This is the molar mass of deuterium. 2 kg means this many number of atoms will be there. The energy released per 2 nucleons they are given. Okay, so 3.21 divided by 2 into this many atoms. Okay, this is the mega electron volt. Time period, that is in seconds, and you after converting to year you will get this many. Calculate the height of the potential barrier for a head-on collision of the two deuterons. The height of the potential barrier is given by the Coulomb's repulsion force between the two deuterons when they touch each other. Assume that they can be taken as the hard spheres of the radius of the 2 femtometer. Distance between the two plus 2. Okay, 2 femtometer plus 2, 4 femtometer. So that is 4 into 10 power minus 15 meter. Femtometer to meter. Charge on the deuteron is 1.6 in 10 power minus 19. Okay, the potential energy is 1 Coulomb's law, 1 by 4 by epsilon and charge into charge. So charge square divided by the distance. Okay, then you will get this. From the relation, the radius of the nuclei equal to constant in the atomic number power 1 by 3, where R0 is a constant, A is the mass number of the nucleus. Show that the nuclear metal density is nearly constant independent of the atomic number. Atomic mass. Mass by volume. Mass. This is a number of nucleons, capital A. Then this is the mass 4 pi r cube. R equal to R0 into A power 1 by 3. So this will be cube. When they cube, then it will become A. This A will cancel out. The R0 is a constant. So here this is independent of this atomic mass. Okay. Okay, this relation. Okay.